minus 5J. And this is in feet per second. Right? And we are also aware what is given to us is the acceleration at point A, again, is equal to minus 7J feet per second squared. Okay. Now, we are also aware that points A and B are under linear motion only. Okay. They are only under linear motion. Okay. So remember, we wrote that acceleration is equal to A tangential plus by A normal. Okay. If under linear motion only, AN is equal to what? 0. Right? So we can drop what? The normal component. Okay. So from here, what we're going to determine is we're going to find omega AB, and we can do this by using instantaneous center, right? So a quick revision, a short revision on instantaneous center. So point A, okay, I'm going to draw in green, is where we construct instantaneous center. So I draw a horizontal line because we are aware that the velocity vector of VA is coming down this way. Okay. And then we are aware that VB is going to a horizontal line, and then we construct a vertical line relative to VB. Sorry, wrong color. All right. So this is our instantaneous center. So when applying instantaneous center, we are aware of this fact, right? Omega ICA is equal to omega ICB, and this is also equal to omega AB. Okay. So from here, we can identify what is our omega AB now. Okay. So before we can do that, we know that we have our VA is equal to omega ICA, and then we are going to find the distance IC to A. Okay. Now, I have email from students. When is it a vector? When it's instantaneous center analysis is based on what? Okay, it's just based on magnitude. Okay, it's a scalar. It's not a vector at all. Are we clear? Okay. So we know that VA, or we need to find ICA first. Okay, so to find ICA, we know that this is what? 30 degrees. Okay, so ICA is equal or sine 30 is equal to ICA divided by 10. Okay. So from here, we know that ICA is equal to it's equal to 5. Okay. So VA, we are aware that VA is equal to what? 5. This is equal to omega ICA multiplied by 5. So from here, we know that omega ICA is equal to 1 radians per second and is rotating in the anti-clockwise direction. Okay. So we have that information. So from here, let me bring this diagram down. From here, we write down the expression AB is equal to AA, okay, plus by alpha cross RB from A minus by omega squared RB from A. If I'm going to write up the full form, okay, if I'm going to write up the full form, okay, so we know that AB, okay, T plus by AB N, this will be equal to AAT plus by AAN, okay, plus by alpha cross RB from A minus by omega squared RB from A. Okay. To make matter worse, okay, this is just one part of the issue, okay. To make matter worse, we know that ABT can also have ABT in I plus by ABT in J. And again, ABN can have I and J component. Not for this case. I'm expanding it for the worst situation for you. Okay. It can also have AB and I plus by AB and J. Okay. And again, AAT, right, can also have AATI plus by AATJ and AAN. Okay, some of you might say, thank God we're not going to be tested this tomorrow on Wednesday, right? Okay. So for the fact that we have what? We have only what? So given to us, right? So we know that these are the possibilities. Okay. But for the fact on what you see over here, point A and point B are what? Under what? Linear what? Motion. So when under linear motion, these two disappear. Very clear. So point A is going through a linear motion. Point B is also going through a what? A linear motion. Why linear motion? Because at point A, if we have a transformation down here, this is our X and this is our Y, this is our I and this is our J. At point A, we know that X is equal to what? 0. At point B, we know that Y is also equal to what? 0. This forces the system at point A, at point B to be under linear motion. That is why we don't need to consider what? These 2 points. Okay. So likewise, because it's linear motion, if you look at the tangential, right, we are under linear motion, right? So we know that at point B, right, at point B, this is equal to what? At point B, this is equal to 0. At point A, this is equal to what? So it simplifies our analysis significantly. Okay. So now I'm going to use this equation now. Okay. So I'm going to use this equation now. Because of the boundary condition, this expression will be simplified, right? So because of the boundary condition, okay, so we know that this can be, you can drop this term. You can also drop this term, okay? And then if we look at acceleration at point B, we know that acceleration at point B in tangential direction, we only have the what? I component, right? We only have the I component because the J component, we are not allowed motion in the what? For point B, we don't allow motion in the J component, okay? So now this term will be equal to A T. We only know that there's J. Again, we don't allow motion in the X direction. Then I'm going to write the whole term down here. Okay. So this is the final form of the equation that we need to put in our numbers. Okay. So I want you all to see that this expression over here, in fact, is much bigger. There's more layers. Are we clear? Okay, but because of the boundary condition we have, we eliminate some of them. Okay, and also it's because it's under linear motion. That is why we are left with this final form, which I will call this form our equation number 2. Later on, when we do questions like this, okay, I'm going to show you one of the worst question. When we do question like this, we are going to deal with multiple components. Okay, for now, not yet. Okay, for now, not yet. It's not that bad. It's pretty bad. Yeah, it's pretty bad. It keeps my head spinning, but it's okay. Our hand. Yeah. Right. So now let me get this image over. Okay, now it's the plugging in numbers, and I want you to observe things, okay? Okay. So we are aware that this will not change. Okay. And then we want to know acceleration of A, right, in the J direction. So this is minus 7J. We know that over here, this is our omega, and alpha will go in the same direction. Okay, so when that's the case, this will be plus, and then we will have a minus alpha k, okay, cross R B, okay, from point A. So this is our point A. So in terms of I, so we have 10 cos, yeah, 10 cos 60. Yes. Point B. Wait, maybe I got the direction wrong. So the thing is slightly, sorry, I got the direction wrong. Did I wrote the direction wrongly the other side? Go on. Thank you for telling me. Yeah, I think because this thing is sliding down. So sliding down, I got the direction wrong. Can you change that, please? Thank you for telling me. Hey? Oh, what am I doing today? I'm sleeping. Sorry. So this is positive. Am I right? Anti-clockwise is positive. Am I right or wrong? Okay, so the thing is sliding down. It's going there. Yep, that's correct. Thank you for telling me. Okay. So RBA, okay, so 10 cos 60. You get a pint of beer, okay? So this will be, so this is my 10 cos 60. This is 10 sine 60. And this is I. And then you have minus 10 sine 60. And you have J. Okay, let me check again. So this is 10. This is sine 60, cos 60. Yes, this is correct. Okay. And then you have minus, now omega squared, we know, okay? So this is 1 squared, okay? And then RB dot